Okay, so let's get started. In the morning, remember we were talking about linear logic, but really we're here for learning about programming. So now let's turn that linear logic into some kind of programming language, right? So something kind of related to what we were doing before. And so what I'll do here is a linear Lambda-Calculus. Linear Lambda-Calculus. And so what's that? That's a sort of Lambda-Calculus where there's certain things that I won't be able to copy. So in general, if I were to write the Lambda-Calculus expression, let x be a tau, I could return to you the pair of x and x. Sure, no problem. Of course, if I have something, I can just make a pair of that thing twice. And you would say, oh, well, this thing has the type tau to tau times tau. Right? That's the idea. But in a linear lambda calculus, if you said that circle times, if I have something, then I have two of that thing. That's sort of exactly the point that we don't want, right? So we want to rule out things like this and say, no, you can't be given something and then just copy it willy-nilly. And so I did not talk about that in the morning, but there's rules in linear logic for when you are allowed to copy things. And then so there's this distinction between things that are linear and things that aren't, that have no restrictions on the amount that you are allowed to or have to use stuff. Okay, so linear stuff is exactly once, whereas nonlinear stuff is as much as you want. That's the idea. And so really here, right, I'm going to do a lambda calculus, but I'm not really going to add new language features. Like we spent many days on okay, let's start with something really basic and boring and add more stuff to it to write more programs and make it more useful. But the story here is more about taking some of that stuff and winnowing away and removing some of the things. Right? It's kind of, I'm still writing programs, lambda calculus programs or functional programs, but they fit in this small space of linear things where we have to take care of resources. So I'm not adding new functionality, I'm removing functionality. And the only real new bit is when we say when it's okay to copy stuff. Okay? Sound good? So what's the language going to be? And so I will, try to go through all the different bits and, sort of talk about, well, first, what kind of fits in this space that's related to the lambda calculus, because I kind of mentioned that you have these extra things that don't really appear from the perspective of the lambda calculus, so look at what we do have. And then kind of the opposite of removing programs is look at the typing rules and then add programs to see what is the program that corresponds to pretty much those rules that we've seen before. So these are just going to be the rules we saw before with a few less stuff, but the same rules before. And what program corresponds to this idea in logic, right? So that's going to be the goal here. Okay, so yeah, let's first write down which types am I going to have, right? So what are the types? So we're kind of collecting from before. What was my grammar of types? So remember we had a bunch of things. So what did we have? We had top, 0, and 1 were the base cases. So these were the two different sort of types or propositions for truth and one of the propositions for false. Right? Those are the base cases. What else did we have? Tau 1 with tau 2. We had tau 1 plus tau 2. We had tau 1 times tau 2. right? I'm not going to have par because, well, that just requires extra functionality that we won't have, right? It's somehow, in the lambda calculus, I only ever had one thing on the right. Par only makes sense if I can put two things there. So that one doesn't make sense. Okay? What else? To make up for that, though, I'm going to add functions. So I'll include a function type, tau1 lollipop tau2, which is going to be a linear function that is something and it must use it exactly once, right? So it's sort of like a special case of general functions where I give you a pointer and you do what you want with it, right? There's no restrictions. So it's a special case there. And one more thing that I'll get to, which is pronounced of course tau. And so that's not something I mentioned before. I didn't have time for that. But the idea of course is that you have as much taus as you want. So you can use it as many times as you like. You can copy it if you want. And if you don't need it, that's fine as well. Right? So that's why it's called of course, because of course you have tau. And yeah, there's no restriction. So in general, by default, everything is linear except that one. That's the one real nonlinear thing. Okay? Any questions there so far?
Intentionally dropped bottom?
Also intentionally bottom. So par needed 2 conclusions. Bottom needed 0 conclusions. And so here we need exactly 1. So on the right-hand side of entails, and I'll write sort of the judgment. So before, what's the judgment? I had a bunch of stuff on the right. So here we're going to have exactly 1 thing on the right, which is the normal sort of thing for the lambda calculus. So that rules out both par and bottom, right? Because those are the 2 and 0 cases, which are not 1. Yeah. So that's also gone. And it kind of makes sense because bottom was the neutral element corresponding to par. So if I lost one, I lost the other one as well. But these top 0 and 1 are related to with, plus, and times. And these are all things that we've seen in the lambda calculus already, except here there's kind of, so this is just going to be the sum type is the preview. And the interesting thing is that we see a difference between 2 different notions of products. But we've kind of already seen, you'll kind of see like one is the one we've seen in lectures so far, and the other one is not all that unfamiliar. If you've ever used a functional language, you'll say, well, obviously that makes sense, because it's that kind of normal thing. Okay, but yeah, so both of the par and bottom are gone. And before I said that functions are related to par somehow, and that's the part that we have. We have the part that actually is a function that transforms one thing into another thing linearly without copying it or deleting it, and so we still have that. Okay? So you kind of have par a little bit, but it's very unsymmetric, and in general, this is not a symmetric calculus because the lambda calculus is not symmetric. So that's kind of the consequence of going with something like the lambda calculus. And so here we're going to have one thing, the typing judgments. So this is going to be not too unusual, but the typing judgments, I have a right and an expression of that type. So far this is totally normal. What else am I going to have? I'll have a gamma, which is that same list of variables with the type, and that's an unordered list where the variable cannot appear more than once. But I'm also going to have another environment delta, and the trick is, the game I'm going to play is gamma is going to work exactly like it did before. And so when we see the rules, it will be exactly like it was before. The delta is the resources I have to be careful about. So this is linear stuff, linear, and this is nonlinear. So nonlinear is what we've been doing this whole time, so that'll look the same. But I'm also going to say, how do you manage linear resources, things that you're obligated to use exceptions. Yep. Overloading? So how are we overloading? So I'm saying one thing is linear stuff, and then the other stuff is not that.
Right, so just in terms of normal linear, nonlinear functions.
Well, linear can't copy or delete, so this is linear in the sense of you use the thing exactly once. So it's in the sense, and that's just the note. When I say linear, I mean like linear logic.
Right,
Yeah. How it relates to maybe other definitions of linear in the past. I'm not sure off the top of my head where that linear comes from. Like linear algebra, I don't know. I know there probably is a connection to linear algebra. There's a lot of connections between linear logic and mathematics, and I'm not an expert in all of those things. So I'd say, yeah, go look that up. Okay, so let's look at a few rules. And well, basically how to type check these programs, and we'll sort of figure out what programs we need to write down to for all of those, right? What is the program of each type? Okay, so the first few is, I'll sort of say the generic stuff, which kind of sets the stage on how all of these work before we get into connectives. What? Yeah?
This data doesn't have anything with the earlier data.
What was that?
This data is not related to...
So, well, and before I was just kind of using delta on the right-hand side as a convention. It didn't really mean anything. And so here, kind of again, they're the same structure. They're both unordered lists that look identical. I'm going to use them differently. And we will see, as I start writing the rules, how I'm using them differently. But one is linear and one's not. So one I have to be careful about, and the other one I don't care. And so to get started, right, so, well, we had two rules, right, identity and cut. So let's first look at cut. And so the cut of linear logic corresponds to a let expression in programming languages. So we've already seen let expressions. Right, and let's look at what that one looks like. So the idea is if I've got one thing that's a type, yep.
That is the judgment?
That's the judgment. Two environments. The environments look the same. The separator will be a semicolon. That's how you know the difference between them. And the point is that they will not be treated the same in the inference rules.
So it's an axiom.
It's a judgment. I haven't written any rules yet.
So there's no bar.
No, that's everything in between bars.
Right.
Yeah, it's just the syntax that organizes all my information that I have. Okay, so linear, right? So if I have gamma, let me check how that goes. Yeah. So here, x of type tau, so the idea, right? Well, without writing the expressions, so the cut was something like I made a thing, I used a thing, and then I put those together, right? So I'll want below the line, I will want gamma and delta delta prime, and I should get some of prime, right? So this is like the cut rule, except that I've got a little bit more stuff running around, right? So the difference here is this is the nonlinear stuff, so I don't care how you copy it. So I just copy it to both of them, right? So these are just free variables in scope that you can use however much you want. But the linear things you have to partition to two different places, right? So I've got some resources that I use in one part of my program, some resources I use in the other part of the program. And so here the point is I've got a program that makes a tau and a program that needs a tau, and I want to connect them together. And how do I connect them together? I say, well, just stick the result of this one in for the variable there, and there you go. So that's the idea. So if I have an expression of type tau, e prime of type tau prime, which needs a tau, then if I write let x equal e in e prime, I get a program of type tau prime, and it doesn't need a tau anymore because I've plugged in something for it. Right? Okay. So that makes sense. And then the linearity part, right? So here's what I mean when I say I treat them differently. If you ignore the deltas, this is exactly the rule that we wrote down for type checking a let expression before. Right? The gamma was just copied to both different premises. But the linear stuff you have to be careful about because you don't want to duplicate. Right? So one set of linear things go to one and the other set goes to the other. So that's how they're treated differently and why you have two different environments. Okay. So let's also look at, so this was the corresponding to cut. logic, right? Because I want to connect two things. We also had, what was the other generic rule that didn't really talk about a type? That was identity. That was, if I had a thing, then I have it. Doesn't say a lot. And so what does that correspond to? So let's write down the skeleton of the rule. It was something like, I had a tau, and then I want a tau. Right? So that was the identity rule. In linear logic, we wrote that down. We called that identity. So now let's start filling in the extra details. Right? So what's one way I could put it? Well, here, tau, on the left-hand side, that's associated with some sort of variable, right? These are types of free variables. That's the judgment. Gamma is a list of variable type pairs. So it's that. But there's kind of a choice you could make here. Where does it appear? There's two different spots. Does it appear in the linear world or the nonlinear world? So which one is it? Any ideas? Should it be in the linear world? Anyone think it should be in the linear world? Okay. In the nonlinear world? Maybe? Should it be in both? Well, it can't be in both at once, but in some sense, I want access to both. I want to be able to talk about the linear world and the nonlinear world. So there's going to be two different identity rules, which is accessing a variable in either environment. So here, I'll say that x has type tau if x is some linear resource of type tau. And so this looks exactly like the variable rule we saw before. The only difference is that this is a semicolon instead of a comma, meaning that x is the only linear thing I have. I don't care about gamma, it's irrelevant. So gamma is still irrelevant, but I can't have more linear resources because if this were my entire program, I would drop them. If I'm given some more stuff, those get dropped. And so it should be the only thing, because that's the only thing I'm not dropping. But what happens if I want access to a nonlinear thing? So if I have a free variable in gamma, I should at least be able to refer to it. And how would I refer to it? So I'll say this is 1 for the linear one. And then what if instead I've got something where I've got an x of type tau in scope, and I want to refer to x of type tau, and x was found in my linear thing, and so I've got a bunch of, nonlinear gamma, and I've got a bunch of other stuff that doesn't matter. So what linear things should I have here? None, right? I shouldn't really have any because I'm not going to use them. So if someone gave me a precious diamond, and I just say, here's a chair, then I'm not using the precious diamond. It's been destroyed, and that's really sad, so don't do that, right? So this is empty, which is, essentially I'm adding it up with the access things from the nonlinear world. That means I'm not using anything from the linear, because I don't want someone to give me something. I'm not be empty. Yeah.
So it can be used to just consume things
Yes.
so that they're not rotting on the shelves.
Yes.
Okay.
But like only one thing, really.
Well, one
Yeah.
thing at a time.
One thing at a time.
You can apply it arbitrarily.
Yeah, or like you can put them together.
fire sale,
Like it's
like a-
kind of, it's sort of, this is how you get started. This is picking one thing off the shelf. And then the rest of the connectives say how you do more interesting stuff than just picking one thing off the shelf. But that's what that is. And then this is sort of like, oh, I don't know, something boring. You took a picture with your camera, and you can copy pictures as much as you want. Like those aren't precious resources, so then you're not pulling anything off the shelf. We're saying that. Okay, so let's look at some of these things. Let's start with the sum type, because there's only one of them, the plus. And that one, we'll kind of see. I'll write down the rules. So the rule for plus in linear logic was here, something like this. Tau 1 plus tau 2. And what's that kind of look like from the typing rules we've seen earlier this week? This is like the way we've introduced a value of a sum type, which is I had a thing, and yes, it's one of those two things that it might be. Right? So what was the way we introduced that? So here, it's if I have a term of that type, then I put it into the left, and that's, right, so that was the L constructor on the left. And then I've got another one on the right, it's the same thing. And do I really need to be that careful about delta? Well, not really, because it doesn't really appear more than once up here, and it's just kind of along for the ride. So I'm not really copying or deleting anything in delta as long as E is well behaved. That's kind of like reasoning locally is that inductive hypothesis. Assume at least what I've got up here makes sense for whatever I'm trying to do, and then don't break it. And if none of the rules break things, then it's okay. So the other one just looks like the other side. Tau 2 goes to on the right. I've got an E, and it is T1 plus T2. So that looks a lot like a sum type. Right? And so this was the introduction for sum, is what we would say that is. Okay, so how do we use that? Well, how did we use a sum type? And it's kind of, the things here aren't all that different from what we've seen so far. It's just careful resource management. And so the linear lambda calculus is lambda calculus plus resource management is what it is. Right? So this is plus resource management. And that's kind of the management, that's kind of the big picture, which is, right, we want to talk about resources in the lambda calculus. That's the sort of lambda calculus is the land of plenty where no one cares about how much you've got. And so what if we care? Okay, so how did we deal with something of some type? What did we do? Yeah.
Case.
Yeah, we had some sort of case which said, okay, if you give me one of these summy things, I'll check which of the two possibilities it may have been and then respond somehow appropriately in either case. Right? And so that's what we're going to do here. That's an R, that's an L. Yeah. So the right or the left. So the case, well, what did that look like? So I'll kind of just write I'll forget about the environments at first, and then we'll fill in what are the appropriate environments. So here, if I've got a case, E of L x goes to E1, and Ry goes to E2, right? So this thing is a tau if, well, E should be a sum thing, a sum type, tau 1 plus tau 2, and then I've got the E1 and E2. Okay, so what were the types of the responses? This is kind of like an if-then-else, but a fancy if-then-else, right? So these need to return whatever I'm expecting out of this, right? Because one of them will be run. So these both have to be a tau. I'm going to need more room over here. Those both need to be a tau. And now we should think about what kinds of things are in scope. Right? So we've not actually talked about the resources yet. This is just the typing rule for a case when there aren't any free variables. So what if there are free variables? So we can just plug in the gamma part, which is nonlinear. We already saw how that worked. That's exactly. And so that's just, well, if I've got a gamma, then it's in scope in both. Right? Gamma is in scope for both, right? That's the idea. But then what about the other stuff? Right? So I might have some deltas, first of all, and then I have to say something about the types of x and y in here. Okay? So what about delta? That's the first thing. So what if I have some resources? And now here's kind of that operational question. What does this do? This program will evaluate E until it sees one of the two possibilities. and in whichever case it is, it will run exactly one of these branches, right? So if I'm given some delta resources, in general, should I split it up between the branches, or should it be shared among both branches? So it should be shared, and the reason it should be shared is I need to use all of delta, and I will only ever get the opportunity to run one of those two, because whichever one I run depends on what E eventually becomes. So this is sort of an operational understanding of why some things will copy an environment, but you're not really copying resources, because only one of the two premises will actually be used at the end of the day. And that's kind of the idea. Right? If you copy stuff, it's because one of those two branches, right? It's branches, not two things. So here I've got a delta in both. And then what about x and y? Those have types tau 1 in this case for x and tau 2 in that case for y. That was the rules for some. And so where do those go? And I'll put them in with delta as a linear thing. Right? So for all of these type constructors, they're kind of hereditarily linear, which means you can only use a value of that type once, and they hold onto values that are linear, and there's going to be the one exception to that, but everything else stays linear. So, this is going to be x of type, don't have a lot of room, let's make some room, x of type tau 1, tau 1, E1, and x of type tau 2, or y of type tau 2 in E2. Y type tau 2 in, I need the delta 2. Delta y of type tau 2 in E2. Okay. And then the delta, actually, now here's a question. Did I do this right? So what if I do this? That makes sense. So using the idea of when I run an expression, it uses up its linear resources, and then they are gone. So does this rule make sense? Or is there a problem? Yeah?
I mean, you need to split delta between E and E1.
Yes. So this kind of, exactly, right? So you need to, there's some splitting and some sharing, and so this is a good opportunity to see that difference. So these rules were kind of boring with regards to sharing because there's nothing all that much going on. But in some sense, right, I said, I will run E, and then depending on what E was, I will run exactly one of E1 or E2. Which means if I said this, once I've run E, delta's gone, I've used it up. Right? It's sort of ephemeral memory. And I would have a problem to get when I get here because I wouldn't have delta anymore. So really what I want to say is that this is some delta prime over here. So it's shared here because only one of them will be run, and exactly one of them will be run. But that's after running this. So E's already eaten up delta. I need to have some delta prime left in order to run one of the two other branches. So some sharing, some sharing. So really, gamma, it doesn't matter, it's just free variables in scope. But then here's two sets of linear resources, one for figuring out E, and then one for running the appropriate branch. And they have to be the same because at compile time, statically, I don't know which branch is run, so either one has to be prepared to use the same resources that are left over. Right? So that's why they're statically the same, because without running a program, I don't know which one will actually consume stuff. Okay? Good. So that was plus. Let's go on to with. Yeah?
In this case, actual part
Because I said I want the pieces to be also linear. I'm making a choice. You could make it not. I want it to be linear because I want it to be preserved. Yeah? Yeah. Yeah. So it's not that it's wrong to put it in gamma. It just says, I've looked inside of a plus, there's no guarantee on whether or not you are linear anymore. So linearity is something that's easy to lose and very hard to get back once it's gone. So it's more informative to say that it will probably still be linear, and then we'll see when I want something to not be linear anymore. But once something is not linear, I can't just make it linear. So one way is easy, the other way's hard. And so I went with the way, I've set it up so that the hard thing is the for free thing, and the easy one you can generate from that. Okay, are we good? Okay. Now let's look at width. And what's width? Well, clearly that's some sort of product type, if we remember the rules from linear logic. And so let's look at the introduction rule from linear logic. No, actually let's do tensor. I'm going to do tensor first. I think that's the easier one. So the rule for tensor was something like, I've got tau 1 times tau 2. So probably need more room. Tau 1 times tau 2. I've got one of those things if I've got a tau 1 and I've got a tau 2. Okay, so there's both the environments and the terms. So does this look like something from programming languages that we saw earlier? This is kind of like a pair, right? If I have one thing and another thing, I can always get the pair of those two things. That's no problem. So let's suppose I've got two things, E1 and E2. Construct pair E1 and E2. Great, that makes sense. Okay, and then what about the environment? So there's going to be just some nonlinear stuff floating around. This is the semicolon that's separating the two things. Okay, so if I just wrote that minus the semicolon, that's exactly the rule we had for pairs before. So nothing that fancy, but how does this? And here it sort of matters, like it's a story of evaluation. Resources are used up by evaluation, so I should come up with a story of how do I run this to use up whatever's here? And so how do I run a pair? There's kind of a choice, isn't there? There was like eager pair or lazy pair. So what if this was an eager pair for now? What would that mean? That would mean to get a value out of this, I would have to run E1 until it becomes a value. I'd have to run E2 until that becomes a value. And then I just put the two together, and that's the result. Okay, so what does that mean? In some sense, to run E1, I need some resources for that. And then to run E2, I need some other resources for that, like fuel. These are two cars, and they both need a separate fuel tank. So fine, okay, I've got one set of resources and another set of resources. And so to run both cars, I need fuel for both tanks. Yeah. So this is delta 1. Right, so it's split. And you can kind of see, oh, there's like an operational reason on why you might want to split your precious resources between two different things when you've got a times rule. Yeah, question?
So you see that delta 1, delta 2 necessarily disjoint?
Well, they're going to be disjoint in the variables they use. Those variables might happen to be of the same type. I don't care. But the variables mentioned here and the variables mentioned there have to be different because one of the restrictions on environments is that I don't repeat a variable. And so by the fact that I could put them together in a sensible way means that I don't mention x twice in both of them. And x, well, I might have an x and a y and they're both numbers. That's fine. That doesn't matter. But I can't say x twice. And that was like a general rule of all of these environments. You can never mention a variable more than once because it was a type assignment. And you don't want to just keep adding more redundant information. And so that kind of separates, right? The linear resources that are in scope for E1 are completely different from the ones in, did I write E1 as well? That should be E2. They're completely separate. And that's kind of, this is what's making it linear. I wanted it to be linear, but it wasn't anything yet because I haven't defined it. And now this definition is what's making it linear. Okay? Now, how do you use these things? Right, and I sort of said this was tensor. So what was that rule for a tensor? Right, the rule was if I've got, well, let's see, how do I use it? And kind of the idea is, if this is linear, and E1 and E2 are linear, how do you use them, right? You have to use both of them. You don't get to pick one. And so this is different from the products before. Right? And that would be kind of a problem. Those said I could project out whichever one I felt like. That means I would be dropping one of these two on the floor. So if E1 and E2 themselves are precious resources, projection just does not make any sense. Because I would be allowed to say, take both of them, drop the second, I only want the first, and the second would fall on the floor. And we don't want that to happen. So what can we do instead? So the rule for, I'll say that the rule in this sense for a tensor looks like if I've got, some tau 1, I'm going to make some other thing. So this is kind of like the left rule plus a cut. So the idea is if I've got some sort of tau 1 times tau 2, I want to use it somehow. How do I use it? Well, I could always add both of them into the environment of some other term that knows how to use them, right? So if I've got someone else that wants both a tau 1 and a tau 2 at the same time, I could unpack this pair and head both over as separate things, right? So it's an unpacking kind of operation which separates some resources. So here, you'll have if x has type tau 1 and y has type tau 2, and well, that lets me run some other term to get a tau prime. Then I can plug them together. This is E, right? So we're kind of slowly stitching together what the story is. So that's kind of the idea. I want to run E, get something that looks like that, and then plug in the two parts for x and y. Okay? So what other kind of resources are running around? So first of all, can E and E prime share the same precious resources? Not really, because I have to run E to get the two things I needed to run E prime. Right? So I have to run both of them to finally get the result. So I need two different sets of resources, delta and delta prime. And then the other stuff doesn't really matter. The nonlinear stuff we don't have to be all that careful about. So that's kind of the same as before. And so what does this look like? So in the conclusion, what do I have? Well, okay, I've got gamma, precious resources I need to do this whole thing. I'm going to need delta to get a pair. Right? I need to put a delta in to get stuff out of E. Right? And I need to put a delta prime in to get stuff out of E prime. Do I need anything about these? Are these things I kind of need from the outside world? Not really. Both of those things came from E. Right? So I really only need delta and delta prime in order to somehow I need to combine them. And I'll do that with another kind of case. Instead of saying which of the two possibilities, I would like to extract the two parts. So this is a case on E of x and y goes to E prime. And if you've ever used functional programming languages, you might recognize this as just another form of case or match. Some languages use the keyword match. Okay, well, I can match on a sum, I can match on a Boolean, I can match on a pair. Right? And so this is a sort of perfectly normal thing to do from the perspectives of running and writing functional programs. and it connects up with linear logic to kind of have this idea of, well, what if I have an eager pair? How do I use that without squandering resources? And it looks like a case. Okay. Any questions there? No? All right, so let's move on to the other kind of product. Question?
You didn't need the delta prime to get the e-prime. You just needed the x and the y.
Any environment might be empty.
Okay, but then on the bottom, so you still don't need the x and y.
You still don't, no matter what, you don't need the x and y. So this is, in general, this is what it is. Any environment might be empty. That's one of the special cases. But why don't you need the x and y? Because those are extracted from E. They're getting bound here in this program. In the same sense that for let, I don't need the tau in the bottom. I think I wrote a tau. Yeah, I don't need the tau in the bottom because that's gotten from E. Right? So that's the kind of idea.
E prime expected dependency on x and y, right?
Yeah, and they're bound right here. Yeah, and they're going to come from here. So when you run this, I expect to run E. I really should get something that looks like this, and then I'll plug in those two things for x and y in order to resolve the case. So that's why I don't need x and y from the outside world. I have everything else I need right here. So that's self-contained with respect to the x and the y, because I know where to get them from. I just need to compute to get those things. So it's not that it's easy, but I can do it. All right, so the other one, well, what's the point of the other one? Well, the idea there is, what if I do want a product with projections? How does that make sense? I want a pair of two things, and I can access whichever one I feel like. Right, that's kind of the sort of pairs we had to begin with. So how does that interact with being careful about resources? So the rule there was, if I had some E, and I'll say it has type tau 1 with tau 2. If that was a thing I had, then I should expect to be able to project out the left thing. And then I get a tau 1 thing, right? So that's just the rule for pairs before. That's a rule for projection that we had seen. And similar for the right. If I have a pair of tau 1 and tau 2, then I can always get the right-hand thing, the tau 2 thing. And so what are the resources that I need for that? Or rather, does kind of anything interesting happen for resources here? In some sense, this isn't a pair, but if I computed it, it would be a pair. So I just need whatever resources that E is, and then I get whatever out. Okay? So here, this is gamma delta, and then gamma delta. Okay? Does that sound good? Yeah? Aren't I dropping one of them after the projection? So the idea is, well, that will incorporate whatever I need to make those things, right? So I compute it, and this is sort of, I need the resources delta in order to compute either one. That's the idea. That's the resources I need to compute either one of the things. So if you want the first, you need the same resources. If you want the second, you need the same resources. This was like the menu. I can make a fruit salad or a smoothie from the same collection of resources. So asking for one or the other isn't dropping anything. We'll sort of kind of get to that, the introduction rule point, right? That, that's what's going on. Was there another question? Oh, okay, yeah.
This is like the two with the limbs.
Yes, this is like the with the limbs. It's a little bit different because it's Lambda-Calculus, but that's what it's like. This is the tensor lim, or the times lim.
Okay.
And it's like, it's kind of like a cut plus a times lim if you want to connect those dots more formally. But that's what that is. Okay, so what about how to introduce how to introduce one of these things. So first cut, does this make sense? What if I just replace this symbol with an ampersand? Would that make sense with the story? Not really, because if it did, I would drop one of these two things, and that's what I don't want. I don't want the opportunity to drop things. Right? So, really what it is that idea of potential. I could return one of two things, depending on what you are actually asking for. So I'm going to essentially write over this rule. So the point is, I don't know if you're going to ask me for the first or the second, but either way, I'm going to have to use the same resources. So here, the idea is like this. If E2 and E1 are two different things that I could use what I've got to make, then it's up to you which one I do, right? I'm giving you a choice of how to use what I've got to make one of two things. So the resources I need are the same, because I don't know which one you're going to pick yet, but it's still a product because I have the potential for two things, which is different than I have computed two things. Okay, and then to distinguish this a little bit better, I'll write that with curly braces, E1, E2. Or even here, let me do a better job. This was L to E1, comma, to E2. To be very clear, T1 with, or tau 1 with tau 2. And the idea is, if you ask me the first for the left, I will do E1. If you ask me for the right, I will do E2. But I can't really do anything yet because I don't know what to do, and it wouldn't make sense to go and eagerly do it, because then what if I guess and I say, all right, I'm going to do E1, and then I run out of stuff, but it turned out you want the second thing. And now we're in a jam because I ran out of my stuff. I can't do the second thing anymore. I was very eager to make you a fruit salad, but you came in and said, I hate fruit salad, I want a smoothie. And I'd say, oops, I don't have that anymore. So you really have to wait until someone asks and tells you what they want before you go ahead and cook it. Yeah?
This is really like tugging at my either intuition as if it's like a sum type.
It is.
It's
like a product, right?
yes.
That's because of the symmetry, right? And so linear logic, even though it's not fully symmetric, it still gives you a much clearer idea of the symmetry of if products and sums really are dual, how are they actually dual, right? And this is the one, remember, with was dual to sum, but tensor was, the pair was just a different thing, right? Times isn't really related to plus. In that sense, they're not mirror images of one another. And that difference mattered, and you kind of see that here. This feels a lot more like a sum. It's just like the other way around, where here, the program making a value gets to pick whatever it wants. The context consuming the value, the eliminator, has to be prepared for either case just to be sort of pessimistic. No matter what, I can respond appropriately. And this is the other way. Right? It's the context or the eliminator or the consumer that gets to be bossy. And so the program that makes the results has to know what to do no matter what was asked of it. So those two things are extremely closely related. And this is just kind of like a different thing. It's also a pair. It's just a different kind of pair. It's not really related to sum of another thing. And that's, so this is the thing that is dual to sums. And the times is not. The relation, though, is that this is an eager sort of thing, just like the sums are kind of like an eager sort of thing. We compute them to get the result, and this has to be lazy. So times is like plus in that they are both eager, and there's got this eagerness, whereas this one has to incur a delay. Right, so that's what makes them different. Yeah? Question?
Is eager to static analysis where you have no determinism?
Well, there's no...
Branches could have been there?
Kind of, yeah. So there is, I guess you could call that non-determinism, and it probably makes a lot of sense in that sense. So at runtime, this is totally deterministic. But before running, I don't know. Statically, there's kind of like a choice that's made that you don't know, and it could be either, and you can't really just figure it out, right? You really have to just be prepared for either.
Statically meaning like from the type checker perspective.
From the type checker perspective. So what the compiler sees, and the compiler doesn't want to run your program because it doesn't have all the arguments yet. It doesn't have your environment and any other input. Yeah. So there's that static. This is the statics part, right? We would like to infer what we can from programs without having to run them because, well, in the worst case, they might not ever return or they might do weird stuff, and I don't want my compiler doing that sort of thing. And then the dynamics, it doesn't have to do with this, right? It just kind of works out because you can actually run things and get results. Okay, so, well, that was the main connectives of the two different products and the sum. So let's see, what's left? Well, we've got the linear arrow, and well, thankfully, we've gotten through most of the hard parts because the linear is all that different from a regular arrow. Really, we're making the hard part of what is linearity, and we've already explained that of other stuff, and we just use that. Yeah, question? Because Lambda-Calculus doesn't have par, because I've only got one conclusion, par needs two conclusions, or needs two things on the right-hand side. That's sort of, at least at a dumb technical level, that prevents you from doing it. I need to be able to fit more than one thing on the right-hand side, or at the very least explain what that means, and I'm not going to bother here, because that's really complicated. I don't think anyone knows what it means yet. Basically, and I'm certainly not going to just figure it out while I'm doing a lecture here. But we can at least look at the stuff that has a really crisp and obvious story in terms of, well, yes, that I use every day, and resources kind of make sense, so sure. And so I have to explain functions. So the introduction of a function is pretty easy. Type tau dot e. And I want to turn a tau linearly to a tau prime. That's the idea. Tau gets converted into a tau prime. Well, then certainly e should be a tau prime, right? The result of the function should give me the kind of thing I expect. And gamma up there, so the only thing missing really is to figure out where does x go. I have a linear environment and a nonlinear environment, and this is meant to be a linear function which cannot duplicate or delete its argument x. So where should I put it? In the linear one. So an x of type tau. Yes, I did not remember prime here. Okay. What about the other linear stuff? Does that matter? What if I have more linear stuff? It's just kind of along for the ride, right? If there's more linear stuff, just here's another linear stuff, right? So aside from this semicolon distinction, this is exactly the way we introduced a lambda, except I'm distinguishing linear and nonlinear stuff, and the entire... Now that I've got a set of linear things, that's where the argument goes. So that's the easy part. So we've engineered it so this really hard thing becomes easy, and everyone else has to organize to make sure that that really is what's going on. But yeah, so that's how you make the function linear, is you have to have a notion of linear, and that's where you put your variable. Okay, so then what about application? So how does function application work? So if I've got an e which turns a tau into a tau prime, and I've got an e prime which is a good tau, then I can apply them E applied to E prime should be a tau prime. That makes sense. Thank you. That should be a lollipop down to 0. Yes. I'm full from lunch, so I'm not thinking about lollipops anymore. Right, deal with resources. Well, the gamma part, what do we do with gamma? It's kind of the same as before, right? So I have a gamma here and it's just up there, and there's nothing that new about gamma. So I've got a gamma, and I've got a gamma. Okay, so what about the linear resources? Should I use the same set of linear resources for both of these? Does that make sense? No. Why does that not make sense? Yeah, I have to evaluate the function, and I've got to evaluate the argument. And so I need different resources to do those two different things. Because to do a function call, I don't really have a potential of one or the other. I really have to do both to do a function call. Right? I have to evaluate the function. I have to evaluate the argument. So therefore, I get two different sets of resources. And so to do the whole thing, I need both. So you list them both on the bottom. And these are the collection of resources you need in order to do function calls. Okay? Yep. Yeah.
Why do we evaluate anything there? Do lambda value?
That's what I will need to evaluate the body once I've got an argument. So the body might need some stuff. So to evaluate E, I might need some stuff to evaluate E in addition to X. And that sort of, so it's not totally precise of like what I need to evaluate to get the value and then I'm done, but I might need to continue on and do more stuff, right? So here it's not just I evaluate the lambda and okay, I'm done, but maybe I have an argument, I have to apply that argument and then keep going. And what do I need to keep going after being applied? Yep.
How can it be that a delta is just along for the ride?
Well, it's along for the ride in the sense that when you apply this function, right, you'll be given an x, but then you'll also have some more stuff, right? So this x is going to be taken from here, but then it's also given some delta in order to compute the result. So if this is the lambda rule, yeah, so it might be somewhere back and forth, but it's a little bit just an intuition for now, but that's the idea. Okay? Yeah?
Maybe I'm wrapping my mind too much into the culinary analogy.
Okay.
Which I like. I was thinking about the lambda comes obviously from the function. I'm thinking, lambdas are abstraction. That's really a formal argument. It's not a real thing. It's like, oh yeah, of course. So then is the recipe for the burger is a double lambda. You have the bun, x is the bun, y is the b.
Yeah. Yeah.
And that will come, the abstraction will come from the evaluation of the delta there, because it's of the delta.
Yeah. That's like if I've already been given.
It's applied to the actual arguments.
Yeah.
Those are the resources that get consumed.
Yes, or that's kind of how you can separate those two phases. So this is a phasing distinction, which is maybe I'm given a bun, but I don't have the beef yet.
Yeah.
So I could be like a function, a linear function, that if I were to have beef, then I could make the hamburger. It's like a partial application. Yeah, it's a partially applied recipe. Or maybe the other way around. I'm given the beef and I've cooked the hamburger, but oops, I need the bun, right? So I'm partially applied, and once I get the bun, I can finish and make the hamburger. And that kind of lets you like take one argument at a time, and you know that's the separation. Yeah, question? Not yet, although I'm highly suggesting some stuff. Yeah, but so this kind of, you'll kind of force the hand a little bit if you want everything to be used just once, in a sense. You say like, I really should just use that once. Yeah. And it kind of forces you a little bit on eager or lazy. Yeah, but that's, I haven't defined the dynamic yet, but there is an interplay. Okay, good, yeah.
When we do the let, if our
Yeah.
We have to add an x of type tau to our resources.
Yes. Yeah.
When we use a function, we're using something of type tau, right, in the
Yeah.
evaluation of the function.
Yeah.
We don't add that to our resources.
Wait,
Is there a reason why we don't do that?
when you say we don't add it to the resources, in what sense?
Maybe I misread. I'm looking at the one we just did.
This one?
No, below that.
This one.
Yeah.
So that's like kind of happening by the dynamics. That's what's going to fill in that missing information, right? It's I would like to, but I need to actually compute it first. Yeah. So this is kind of the how do you connect those dots, right? So clearly I could plug in things that are free in delta, but like the argument of a function, well, that's a binder inside of my programming language. I can't like come in from the outside and plug into it, right? So these are the outside world, but then there may be internal binders, like here, an internal variable, which I don't know what that is yet, and that someone else can't come in and say, oh yeah, x is 1. How do I do that? Well, I apply the function. So that's happening here. In the dynamics, right, when I have a lambda, I plug in that thing for the lambda. And that's where that's headed. Yep?
So we assume then that the argument is already captured in the delta.
The argument is already captured in the delta. So the argument is going to be plugged in for x in delta. So the missing parts are the rest of delta.
No, I'm saying in the actual application.
Yeah.
It's now already.
Yeah. So what's going to happen is I've got the other delta stuff.
And also the x.
And then there's also this x it needs, and the x is going to come from here. That's the idea. Yeah. Okay, we're almost there. The last thing to explain really is that bang, the of course, and so far, right, for everything we've seen, everything we're assuming is a precious resource, but what if something's not really? Yeah?
It's an axiom.
What's an axiom?
And of course.
Kind of, yeah. So it's sort of like and when you're doing linear logic, it's sort of like the facts that you can do as much as you want, right? So like, maybe in some sense, if I've got a printer, paper is a resource, and it matters how much paper I have, because if I'm out of paper, I can't print anything. But the printer itself, in like a physical sense, right? I can use that printer as much as I want, as long as I have the paper to run and the ink to run to go in and get some stuff. So in some sense, the printer is, a mapping. Printer is a mapping from paper and ink to, I'll call it a page, right? So it's paper with ink on it. Does it matter how often I use my printer? Not really, right? So paper is a resource that when you use it, it's gone, and the same for the ink that goes on it. But I can use a printer as much as I feel like. I don't use the printer once and it like breaks down and evaporates. And so that's what of course is for. Like, of course, yes, a printer turns paper and ink to a page, and you can keep calling printer as much as you feel like. There's no restriction. This is like exactly what you want that for. You don't want everything to be ephemeral because, well, some things you just don't care about how much you use them. And so that's the one type that is doing this. So because linearity is hard to recover once it's gone, everything sort of. But when you don't care about linearity, you can just throw in a bunch of exclamation points, and it's not linear anymore. Yeah?
So in the food example, would you need to define lunch as a thing if you wanted to serve many people?
Well, that would be quite a magical kitchen, because what that's like, we'll kind of see the rule in a second. But what that's like is I've got a restaurant where I can serve an infinite amount of lunch, no matter how many people come, even if the entire population of Brazil is here. I can feed Brazil, sure, no problem, right? There really isn't a limit, so maybe you want like an upper bound on how many people you're willing to serve. So the of course really is like infinite. I have there's no limit on how much you can ask me to make. So that would be the magical kitchen that can serve the entire population of the world. So that's, you probably wouldn't want that to be, you probably wouldn't want to be in charge of that kitchen because that sounds like a nightmare. But what are the rules here? And so let's kind of, well, we can, the explanation of that is why that kitchen job would be very hard. Right? So how do we introduce and use one of these things? Right? So suppose, let's write it over here. So let's suppose I'm capable of making one thing from some, so let's suppose I write this, E, and I'll write the introduction form in my program as gamma delta many E, where the reading of this is, if you can make one thing, you can make as many things as someone asks for you. Right? So this is like, if I have $1, do I have as many dollars as it takes to, buy? Probably not. So this would totally break that idea of linearity. But when would that be okay? When is it okay to say, if I've got one thing, it doesn't I have as many as you feel like? Right? So I kind of want to say, when is that an okay thing? Well, so what about in this case? What if I don't need anything precious to make something? What if I can just fabricate it from unlimited resources, or resources that aren't restrained? Could I then make as many as you want? The idea is sure, because I didn't use anything interesting to make it. So if it turns out that E, I can make one thing without consuming any resources, then it doesn't matter how many of those I make. I don't have to make anything because I'm not obligated to use any resources. I can also make it twice because I don't need any resources to make it. So I can make many E's as long as it doesn't require anything interesting to make it. Right? Okay. And so, well, what's the usage form, right? So how do I use something that's a many thing? What's that look like? So what if E, what if E is, well, of course you've got some taus, right? And the idea is, what does this mean? If I've got as many as I want, and it's kind of like the let, and it's kind of like this, right? If I've got some stuff, I want to look at it and use it somehow. And here's the difference, right? If it doesn't matter, E is capable of creating as many taus as desired, right? The idea is, well, you can unpack this many, just kind of like you unpack a pair, or you case on a sum. So case E of many x goes to E prime, right? This is interesting because I want to say someone else is allowed to ask for as many copies of tau as they feel like. And how do I express that? So this is going to be some other sort of thing. So that means E prime, or E prime, is a tau prime, and, right, it's going to use x as many times as it wants without restriction. Remember, this was a linear versus nonlinear thing. For the purposes of E, it wants an unbounded access to x, or an unrestrained access to x, which is going to be, what is that? Some sort of tau. Right? So it's what if I want a program, right? So far, everything's just really been in delta, and we haven't done anything with gamma. So what if I... And that's what's going on here. To introduce or set up this binding of, I want as much stuff as I feel like. How do we do that? And that's the idea here, which is adding x to my unrestrained set of just things in scope. And then it's a tau because it's sort of the contents of the many, right? It's not just capable of making one tau, it's capable of making any taus you want because it didn't need resources. So this is the how can I do duplication without accidentally duplicating other stuff? Or how can I do deletion without accidentally deleting, important documents? Right? And the whole point is that E contains no important documents, so you can delete it. It doesn't matter. It doesn't contain them, or it doesn't need them. Okay. So then what about the other stuff? So gamma is shared by all of them. Boop, boop. What about the rest of the deltas? So this is very similar to this rule down here. Let's see if I can get them both on the screen at once. Yeah. Okay, great. So it's very similar here, except that instead of saying the interesting part is that I've got two things, the interesting fact is that I've got unlimited stuff. It's the same thing, but I can use it as much as I want. Other than that, the deltas are very much the same. I've got to evaluate this E here, and then the E prime there. So the deltas are different. Delta and delta prime. And so those are all listed in the conclusion. And that's the rules for duplication when you have to be careful. Okay, a question? Shouldn't delta be empty set? And so the reason why I did it this way is it's sort of like I'm setting up a hypothetical scenario that I hope never happens. And that's kind of, how I've arranged it, which is think pessimistically, in a sense. I'm running this, and what could that be? It could only ever really evaluate to that sort of thing, which means that it's going to have to be empty. And you kind of discover that by running your program. And so, just to sort of, I'm not stipulating it here, but it doesn't matter because it's stipulated there. So in practice, that will always be empty. I just haven't set it there. Yeah, and that's kind of, you want that to be empty. I think you were next. No, it's just syntax arrow. It's not actually implication. I think I may have written a different arrow before, like a double arrow.
Yeah, you did the rocket.
Yeah, I did a rocket. I should probably be consistent and do rockets everywhere. That's just for all of these. There's nothing to do with implication or lollipops or anything. It's just the syntax of programs. It's whichever ASCII arrow you prefer, pretty much. Okay. So that's, I guess almost all the typing rules. There's also the constants. And those are just zero cases of what we've seen before. So, what's the zero case here? It's something you can never really use because there's nothing you can ask of it. Right? So the zero case for width looks like this. Top. And nothing's up here. And that's fine, right? So there's a lot of this kind of playing with fire with logic, and you kind of see what you can get away with, which is this looks like it drops stuff, and it was kind of already there in linear logic. And the reason that's okay is because you'll never actually use it. So it doesn't really matter that you've swallowed some resources, because it will occur at runtime. Let's see, what else? The rule for the zero case, right? So that was kind of dual. So there's no way of using this whatsoever, and that's the point. For top, it's a totally useless thing. Literally, there's no way you could use this thing in any meaningful sense. Zero is the other way. It's an impossible situation. That's the idea. So there's no way to make an impossible situation because it's impossible. That's the point. And on the other hand, right, what do we do if we're in an impossible situation? Well, I don't know. We're in some alternative universe that's not the real one. That's kind of the idea. Or we're in dead code. It's a branch that could never really be invoked at runtime. And I think Jan wrote that as an empty case, which is exactly what it is. Which is what happens if somehow you generate for me E of type 0. That can't happen. So we say, fine, I'll do kind of this pattern matchy thing and say, all right, E is, and there aren't any, and then and it's sort of a challenge where someone says like, yeah, I proved false. And I say, oh really? Well, show me. And the point is, you can't ever come back to me with a good proof. So somehow, well, either you're doing something really wrong, and now the reason why the program crashed is your fault, not mine, or, well, I couldn't have been here in the first place. And so the more common case is sort of you wind up in a branch of code and you realize, like, oops, I assumed that n is both even and odd. I can't ever have one of those things, so therefore there's no possible cases. You can also think of like absurd. Some people say abort, but it's not quite like I abort. It's like I never could have reached this code, like comments dead code is the idea. And then the last one is the unit, right? The other unit for 1. And that's sort of like this boring thing that's around and you have to use it, but there's nothing in it, so you don't get anything out of it. So here, right, what is the rule for if I have an empty tuple of type 1? Certainly I can make an empty tuple, and what resources do I need to make nothing is nothing. So that's empty. So this is why there's that difference between top and unit. I'm actually making an empty tuple, and that requires nothing, versus no one's going to look here. And then what happens if I've got one? Okay, what happens if I've got an empty tuple? Well, you kind of just ignore it because you don't learn anything. So it's fine, I've got an empty tuple, now I'm going to do something else. So that's what happens there. Gamma, delta prime, E prime is something else. Then gamma, delta prime says that case E of it's an empty tuple goes to E prime. That's going to be a tau. Tau, just regular tau. So those are the units. They're just the null area cases of the rules we've seen. Okay. And, well, yeah, we could look real quickly at the dynamics. Is there sort of any questions about the empty ones? These are like kind of the boring cases, but I think for programming, these are the easier ones because there's just not as much going on. Like, yes, I can make tuples, or an empty tuple, it requires nothing. And then to use it, I throw it away because it wasn't really anything. Right? And this is dead code. Right? And that's just, you can't do anything with it, so it doesn't matter. Was there another question? Okay, so let's go on to the dynamics real quick. And I'm not going to write out, well, in that style of all the inference rules on how you evaluate things, because that takes forever. But let's first start with the main reduction rules, which is how to resolve what happens when I introduce something and then use it. Okay, so, well, some of them. So there's a bunch of stuff. So let's say that first I'll say what values are. All right, so what's going to be a value? And so there's kind of like that eager versus lazy thing, and the story of resources kind of dictates when I evaluate things. So for example, it would be wrong to eagerly evaluate the two different parts of a width because they consume all the resources, so I'd be consuming those twice. Likewise, it would be wrong to sort of avoid evaluating one of the two parts of a real tuple pair, so that I have to evaluate those ahead of time. So what do we got? So an empty tuple is a value. Values. Right? A L of a value, right? That was the left constructor of a value is a value. A right constructor of a value is a value. Let's see what else. Lambdas usually are values. So this is like really similar to when we're doing like products and sums in the lambda together, but like here I'm doing it. So this is like so far a call by value lambda calculus. I'm not really doing anything before here. What else? So and so this was what we did for lambdas before, right? So any lambda, regardless of what it is a value. So what about the pairs? L goes to E, comma, R goes to E. Why is that a value? Because I don't know which to run yet, because you need to tell me. So I have to wait until you tell me which one I am before even trying to run one of the two branches. Yep?
Isn't that the opposite of what value means?
Well, when I'm done. Or when I would need more information to continue.
So how do you put a thing that clearly needs more information as a value? Because you know that you need more information? Is that?
Well, or it's sort of like, a number's a value because it just is, and in order to do something with it, I would need to know what I'm doing, right? I can't simplify a number down to anything smaller than a number. I don't know if that explanation helps. In the same sense, why is lambda a value? I need to do something with E? It's the exact same argument here. These are like, I have a choice between two lambdas that don't need any more input besides that choice. So the point is, this is like a lambda, if you really want to make that analogy. But I could not go ahead and evaluate any further if I see one of these things. So even if I'm trying to be eager, I can't go evaluate this anymore, if that was the result of my program, because I would basically use the same resources twice. And that would be a bad thing. All right? Perspective of I want to write a call by value language, but resource use and linearity prevents me from evaluating some things. So just like I can't evaluate EX with E without knowing X, I can't evaluate either of these without knowing which one to do. That's like an argument. Yeah, so that's the real missing piece of information. Okay, so blah, 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 blah. I guess the unit here, also a value, I guess. You don't do anything with it. And then I'll say I had a many. V is also going to be a value. I had that many constructor, which sort of said, here's a value that doesn't need any resources in order to do anything with it. If you want to look at the value, that requires no resources to continue computing. Okay? So that's the definition of values. And so how do we reduce? And it's very similar to, before, and kind of that was the idea, right? We're not adding new stuff. It's really the type system was the real big new thing, and then this is just the same rules as before. So if I've got let x equal to a value in some E, what do? I plug in V for x, right? There's no more checking I have to do, right? So this is E with V for x, and we saw this rule a few times. What about functions? If I've got lambda x dot E applied to some V, the result's the same. I plug in V for the argument. V for x. Okay. Right, and then you can just keep going. If I've got L goes to E1 and R goes to E2, and this is kind of like the hint that it's more like a function I'm trying to suggest here, right? A transformation. It's not just I've got two things, but I need to learn something in order to compute what that thing is. So if I ask for the left thing, I get the left thing. If I ask for the right thing, there's another rule for that case, right? Same for, so there's another rule that's almost identical, but it's an R instead, I get E2. If I have a case, right, there's a bunch of case rules. Case, E, or case in the left of some V of, what was that, in left of x goes to E1, right braces here, and in right of y goes to E2. Then what's the result? Well, it's E1 because it's on the left, and I have to plug in something for x. E1 V for x. Yep.
Is that rocket a step on the...
Sorry, that should be a step, yes. I'm confusing my arrows as I'm writing them, but that is the maps2 step for the operational semantics stepping relation that I'm defining right now. Same as before. So like these are all of the rules you've seen. There's another one for the right case. How does pattern matching on a pair work? Right, so it's got to be a pair of two things, V1 and V2 of, and then it matches against the pair XY in some E. What's that step to? Can anyone guess? Like just your knowledge of what case and programs mean. Was that a suggestion? Anyone?
In V1 substitute for x and y, V1 and V2.
Yes, so it's E, and then I plug in V1 for x and V2 for y. So it's just, I'm doing two substitutions, V1 for x and V2 for y. Right, so I just substitute two things. It's not really that much different from a case. Last bit, there's also one for the unit, right? So if I do case unit of unit goes to E, then that just steps to E. All right, so nothing new there. Slightly more interesting is case many values of x goes to E, and that's E for V substituted for x, and that's interesting because this is the one case where x may be used all over the place in weird nonlinear ways. And that's kind of where I said why you need to make sure that when you're type checking a many thing, there aren't any resources here because it might be duplicated. And the kind of lesson here is that resource safety, like not duplicating stuff, is type safety for this language. So by putting resources in the types say things about resources. And that's the sort of lesson. And so the statement of progress and preservation are the same thing, right? That doesn't really change all that much. It's going to look exactly identical. The interesting thing is when you're doing preservation, that when I do take a step, I don't break type checking, is that kind of has a little something to do with resources. So because I have two environments, one linear and one nonlinear, I'm going to have two substitution lemmas. Right? Because they act a little bit differently. So it's what happens if I substitute a linear thing in, and then what happens if I substitute in and it's used in a nonlinear way. And so the two substitution lemmas are, so the lemma for substitution, so the one case is a linear sort of substitution. So that's where, when I plug it in, the term is defined, the expression uses the thing in a sort of nice way that doesn't try to use it more than once. So if I've got, where is it? So if I've got some gamma delta E, which is a tau, and I maybe need some resources to compute the value of tau, of value E of tau, type tau. And so if that and gamma delta prime x of type tau, E prime of type tau, essentially if I can make a tau, and I want a tau, and I'm not going to try to copy or delete tau, I can just do the substitution. Right? And because it matters where I list how much it's used, what do I get? So if I've got those two things, then what can I derive? So I want to plug in E with E prime with E for x. that should probably be whatever the result of E prime is. But what about resources? And so the hint is, we'll look at the let rule. That's kind of like, let is this fact, but as a typing rule. The fact is that, this will require delta prime to compute E prime, of course, but it only uses this once. Right? This use of a resource is only required once in order to get. So the whole point is that when I plug in a linear variable, it doesn't try to use it once. But what about a nonlinear variable? So the nonlinear case is, so here, you'll find out when doing the proof that if you want to plug in for a nonlinear variable, so if I've got a thing and I want to plug in for a nonlinear variable, tau prime, or tau, with delta prime, E prime, tau prime, E can't use any resources because it may be dropped or duplicated within E prime. So substitution only makes sense, meaning that I don't break resource use if there weren't any resources to begin with, because there's no guarantee here. Right, so the nonlinear substitution has no guarantees, which is why for this to be type safe, V can't have any resources inside of it. Okay, so then the substitution makes sense, and the only resources I needed were whatever E prime uses, E for X. So that's where that restriction comes from. Right? And so kind of the lesson there is that in linear lambda calculus, type safety is resource safety. And it shows up when you're doing things like progress and preservation, or if you prove something about the dynamics, you'll see like resource use come up. And some facts about that. So I'll answer any questions. Yeah? Did I typo? Or? And maybe it's hard to read, is what if the variable I'm substituting for is in the linear environment? That's what this case says. And this is, what if I need to substitute for a variable in the nonlinear environment? And those are different judgments. And so they're just different. They're just like not, one's not better or more general than another. They're just two different things. But the interesting part is that to prove this, right, if this had some resources associated with it, there's no way to predict how many you'll need down here. It may be 0, it may be duplicated twice, 3 times, 4 times, and we count how much that is. And so you actually won't be able to prove the rules that track, like, do I divide it up or are they not duplicated, will break. So it won't even type check unless that's empty in the second case. So they're not quite, one is more general than the other. It's like, I want to be able to substitute for things in gamma, and I also want to substitute for things in delta. And they're kind of two different cases. Yeah. Yeah.
So in a derivation tree,
yes,
it's ultimately what we're doing. We're
yes,
composing a lot of these together.
Yeah.
That just means we kind of start. It's almost like every choice we make, we have to make sure that our inventory, our delta, is like thought through correctly.
Yes, and so like if you didn't, or like you started in some weird state, like you'll get stuck, depending if you're going top down, bottom up, either way, right? It could easily be like, oh, let's see if I've got a rule that separates them. I don't know if I do anymore, but there are rules that separate, this one even. I'm kind of going bottom up. You might say, oh, I've got some resources, and I'm going to try to like divide them, and hopefully that works, but it might not work. And so in general, when you are building proof trees bottom up, this division is an extremely hard thing to like figure out and guess. So it's not to say that this is easy, and probably the easy way to read it is top down. If I've already figured out pretty much everything else I need to know, this is how you combine it. But going from like, this is what I want, and how do I like justify the pieces is hard. Yeah, and so like that division is a difficult thing, yeah. And then so there are tricks to make that easier to do in an algorithm. But like as I've written, this is not an algorithm that tells you how to divide. Just if you guessed really well, it works. Yeah. All right. Yeah.
I don't think I missed this, but like in your type language, you get the next exclamation mark. Does that mean?
I put, what was that?
Like, I mean, you can exclamation mark, some other type would be a valid type.
Right. What if I have more than one? Of course. And there's a lot of fun theory about these modifiers. So just with this, I'm pretty sure only one matters. So if I have exclamation mark, that's the same thing as just one. I can duplicate a duplicable thing. Okay, yeah, sure, fine, that's no problem. In full linear logic, which I didn't talk about entirely, so that this was, I didn't talk about this in the linear logic from earlier, but that was kind of like the symmetric version, and it had some more connectives. It also had par and bottom. So it's got this, but that was totally symmetric. So you might think, what's the symmetric counterpoint of the exclamation mark? And surprisingly, it's not also exclamation mark. It's not sort of like self-dual. It's some other thing that's written question mark tau, pronounced why not tau. And so of course, so this is something that of course is true. And it doesn't stop being true just because you've used it. Or it's a resource I have and it doesn't go away just because I looked at it. And this is, at least in logic, an obligation, a proof obligation that I don't really have to fulfill. It's like, well, why not? Suppose whatever. And so it's kind of the other way around. So it's not like when I'm consuming an of course, I get to say how much I want. Whereas when I'm proving a why not, I get to prove it however many times I feel. Right? So it's kind of like the other way around. And when you've got both of them, then there's some more interesting combinations. And there's still, interestingly enough, a finite amount. Like, you've got that, you've got question mark, and so of course why not is another thing, and why not of course is another thing. And I think there's like some 3 combinations, but then you list like maybe 9 possibilities, and like that's all that matters, which is kind of an interesting thing. So it's related to another thing in logic called modalities, which is like they combine in certain ways, but then you very quickly get a saturation point where you're not saying anything new. So that's kind of interesting, and that's like in the field of logic. There's people who study that sort of thing. Yeah. Okay, yeah. Other panel. This one? Yeah. Okay. So I think I will leave that there for linear logic. But yeah, that's a sort of, how do you do resources? Whereas, in functional programming, you don't care about cost or resource. But that's not always practical. So what happens if you do? Yeah. So that's kind of the story there. All right. Thanks.